Hello, my name is Martin Richter. I'm an assistant professor of applied mathematics at the School of Mathematical Sciences at the University of Nottingham. Applied mathematics, that means we try to use mathematical tools to describe, predict, or improve very complicated everyday problems. In this 30-minute video, I will give you an introduction of what that means in my case in particular, and how we use matrices in order to solve these complicated problems. If at any point you want to know more about that, please come along to our webinar later on. Now, if I say complicated problems, what does this mean? Now, in my case, that means predicting vibrational excitations through very complicated structure. One such very complicated structure is seen here on the left-hand side. It is a car or model of a car, more specifically only the front bit. So our question is, if we excite this car by shaking, for example, by going through a bump on the road, how would these vibrations then propagate through this very complicated structure? And I hope I'll be able to convince you that matrices are a very helpful tool indeed. Now, first, in order to describe this, we have to set for a certain toolbox, a mathematical toolbox. And the toolbox I want to use here is that of dynamical systems. So what is the theory of dynamical systems? Well, simply speaking, it starts from an old data set and predicts new coordinates for this data set. So, for example, if you throw a rock into the air, the x old would be your initial point and the velocity vector with which you throw this stone into the air, and x new would be, for example, the prediction of where it lands in front of you. Now, this theory of dynamical systems can be very complicated, as here seen on the left-hand side for our vibrational problems. For us, it will answer the question, if we have an excitation, a vibration going on here, where does it go following this very complicated structure? So input is mapped to an output. An old position is mapped to a new position. Our vibration will start here and will propagate through this complicated domain. In this language of dynamical systems, all you need in order to understand what is going on is in principle this function f, which maps input to output. Now, we will be applying this function again and again. So starting somewhere, then it will get us somewhere new, and then we will continue from this new point by applying f again. So a more suitable way of calling these variables is with a subscript n. We will start with x0, apply f once. This will give us x1. Then we will apply f again and get x2. We'll apply again f to x2 and get x3, and so on and so forth. And this, in the language of the left-hand side, will then propagate these rays step by step by step through this complicated domain. Our vibrations are mapped forward one time step after the other. Now, for this real-world problem, of course, this f is way too complicated. So in this short introduction, I will focus on something way simpler. And what I want to focus on is the so-called logistic map. I gave it the same color here, so this letter f symbolizes again the function which maps a certain input to an output. And here it's given by 4 times the unknown xn times 1 minus n again the unknown xn. So it's a quadratic function, as you might have already encountered. We allow x to have any values between 0 and 1 as indicated by this array, or as indicated by this arrow of values between 0 and 1. If we pick any initial condition, for example this one, x0, we can readily calculate x1 by applying the above function. And we get, for example, this point over here. And as I mentioned earlier, we can continue applying this function to see where this trajectory is taken by the time going on and on. So as we go along, we get more and more points, and they seem to jump around rather chaotically. And indeed, the system has chaotic dynamics, but that would be something for another talk. Now, this is all fine and well, but the question arises, where are matrices in this? I can't see any for the time being, and we'll have to dig a bit deeper to actually see them here. But before we do, maybe it's a good point to introduce matrices to begin with. So what are matrices? For the sake of this talk, I want to understand any square grid of numbers as a matrix. As the footnote here indicates, it might be more complicated and there are rectangular, non-square matrices as well, but focusing on square ones for the time being will make our lives easier. Here's a very simple one. It has 2 rows, 2 columns. These matrices are also referred to as 2 by 2 matrices, and I put in the numbers 1, 2, 3, and 4. In fact, you could put in any numbers you like. Here's an example of a 3 by 3 matrix. I put in not only natural numbers, 1, 2, -1, but also negative integer numbers or real numbers like square root of 3 or minus square root of 2 or 1.1. Again, because we want to focus on square matrices, this one has 3 rows and 3 columns. Here's one which has 4 rows and 4 columns, and it shows a very special one, namely one which is 1 on the diagonal and 0 everywhere else. These kinds of matrices are very, very important, but we won't go into the details here. It turns out that these matrices do have a life on their own. They're not just nice grids of numbers helpful to display a large set of data on a sheet of paper. No, it turns out that you can use matrices on their own in order to calculate things. For example, if 2 matrices have the same number of rows and columns, so here 2 by 2 and 2 by 2, you can define the sum of the two. And the way this works is you take the leftmost number in both of them, you add these, so 1 plus 7 is 8, and you write this 8 as the leftmost number in your result. Then you move one over to your top right corner, which is 2 here, and the top right corner is 3 here, so 2 times 3 is 5, and this 5 goes into the top right corner of your result. Then you go to the lower left, 3 minus 5 is -2, and so you proceed through your whole matrix and calculate the result element by element. 4 plus 0 is 4. That's not the only thing. You can also multiply matrices with numbers. So if C is a normal number, like number 3, then multiplying this with our matrix 1, 2, 3, 4 means that we can take the 3 in and multiply each of these numbers with 3 on their own. So 3 times 1 becomes 3, 3 times 2 becomes 6, 3 times 3 becomes 9, 3 times 4 becomes 12. So they almost behave like normal numbers. You can also add them together and you can multiply them with numbers. But is this all? It turns out that they only almost behave like numbers. And the most striking difference is what is called matrix multiplication. And I'm going to go through this in an example on this slide. So let's assume we have 2 matrices, 1, 2, 3, 4, and 7, 3, minus 5, and 0. There is one seemingly a bit complicated way of multiplying them by having a look at the result, which again will be 2 by 2, so it will have 2 rows and 2 columns. And the way you calculate each element of this product is that you go, for example, to the first column and first row of the result. You take the first row of your first factor and the first column of the second factor. And then you multiply this number by this number and this number by this number. So you have 1 times 7. By color, you can see where these numbers came from on the left-hand side, and 2 times minus 5. This, of course, you can calculate and you get -3. Now let's go over here. If we want to know this number, we still stay in the first row of the left-hand side factor, but because we are now in the right column of the result, we go to the right column of the right-hand side factor. So now it's 1 times 3 plus 2 times 0. This again are just normal numbers and you can calculate them. The result is 3. Now we go to the second row. The second row in the result means going to the second row here on your left-hand side factor. Because we're now in the first column again, we go to the first column of the second factor, and we multiply 3 times 7 plus 4 times minus 5. This is 21, this is minus 20, so we get 1. The last number, of course, is then the last row in the first factor and the last column in the last factor. So we get 3 times 3 plus 4 times 0. And again, that is something you can calculate, and it's 9. This seemingly very complicated way of multiplying matrices will turn out to be very beneficial. And it is helpful to get used to that should you ever want to work with matrices. This procedure here can be generalized to larger matrices as well. So you can multiply a 3 by 3 with a 3 by 3 matrix. You would again take the corresponding rows and columns of the left-hand and right-hand side factors and calculate these sums of products to determine which numbers go to the corresponding values on the right-hand side. But instead of going into details here, I would like to focus on one more thing, which is the application of a matrix to a vector. So a vector in this sense is only a very special matrix, namely one which has only one column. So here's an example, a matrix 1, 2, 3, 4, like before, and a matrix which only consists of one column, 7 minus 5. You can calculate the product just as before, which is now way shorter, of course, and we get this 7 is multiplied with this 1, plus this 2 is multiplied with this minus 5, giving us minus 3, and then we already go to the second row here, so we need to use these numbers, 3 and 4, multiply them with 7 and minus 5 respectively, and we get 3 times 7 plus 4 times minus 5, and as before, we get the number 1. And this will be very important later on when we have certain initial things to think about and we want to propagate them forward in time, just like we propagated forward our initial conditions in the example of the logistic map. Now that we've set up our matrices, we know what they are, we know how to multiply them, we know how to add them, we know how to multiply scalar numbers with them. Let's see whether we can find out what role they play in our research. That is, how can we use these matrices to understand these dynamical systems better? In order to bring matrices into the game, we can look at the aforementioned range of numbers from 0 to 1, but look in a more broader, coarser sense. So I want to understand what's going on only in terms of left and right. How can I introduce matrices here to help me out? Well, for example, we could think of the probability of ending up on the left or on the right if we start anywhere on the left. So how can we calculate that? An easy way to approximate this is by choosing 9 points, for example, and distribute them evenly on the whole left-hand side. And then we follow each and single one of them and see where they end up. So let's start with this one here. If we map this forward, just like we did before, we will see that the result is here. We can do the same with the second dot, which will end up here. And we can do the same with the third one, which already only slightly lives in the right-hand side. And then we take the next dot, the next, and for each and every one of them, we calculate where they end up. Now, if we only take these 9 points into account, we get a rough estimate of the probability of our final point lying in the left-hand side being 2 out of 9, and the probability of lying on the right-hand side is 7 out of 9. A more thorough investigation, essentially by using more than 9 points, would reveal that the probability of being on the left-hand side, if you start anywhere on the left with an equal distribution, with an equal probability, is roughly 30%. And getting to the right-hand side is roughly 70%. Now this is already very helpful, but can we generalize this? So that was for starting with 100% probability anywhere on the left-hand side. What happens if we start with a probability of 50% here and 50% on the right? What if the distribution is more complicated than that? What happens after 2 steps? These are all things which matrices will allow us to answer. More specifically, we will use a thing called a transfer matrix, because it transfers probabilities from time 1 to time 2. And in our simple 2x2 case, we would write this matrix T as a 2x2 matrix. So we have a 2x2 grid of numbers. The first number on the upper left-hand corner is the probability of whenever you start on the left, you'll end up in the left. The upper right-hand side will be you start in the right-hand corner, or on the right side of your interval, and you end up on the left. And then in the lower left-hand corner of this matrix here is the probability of starting on the left and ending on the right. And finally, in the lower right-hand corner is you start on the right of your interval and you end up on the right of your interval. And using these numbers from before, we can calculate the full T matrix, and this is what we get. So to answer the question, for example, if we start with 100% certainty somewhere on the left, and if we encode this probability of only being on the left by a vector which has a 1 in the first component and a 0 in the second component, representing 0 probability of being on the right, then after one iteration of our dynamical system, the probabilities of being in the left or on the right are given by this matrix product. And this is why these matrices are so important. They allow us to calculate these probabilities given that we know a bit about the probabilistic distribution of where we are at time 0. We can encode what happens to these probabilities as time goes along by the use of these matrices. And if we multiply or apply this matrix to this vector as we have seen before, we take this 1, we multiply it with this 0.29, this gives us this 0.29, and then we add 0 times 0.29, so we stay at 0.29. And then for the lower number here, we take this 1, multiply it with this number, plus 0 times this number, which of course gives us 0.7071067. Now this is all nice, but as I said, there are many more beneficial things to be taken from these transfer matrices. For example, we could right away look at the probability after 2 iterations by just calculating t times t, or sometimes abbreviated as t squared. This is a new matrix. It again has 2 by 2 elements, but it gives you the information of how probability is redistributed after 2 iterations of the time. And this only works, the going forward in time and applying matrices, because we defined our matrix multiplication in this slightly odd way earlier on. This example so far is only concerned with a subdivision of our interval of numbers in left and right. Can we add more detail to that? And the answer is yes. For example, we could subdivide it into a third on the left, a middle bit, and a third on the right. If we would do that, then our matrix is not 2 by 2 anymore, answering where do we go from left or right, where do we go from right, left or right, but it answers if we start left, what is the probability to go left, middle or right. And it answers this for all 3 different places you can now start from. What happens if you start from the middle bit? What is the probability of going left, middle or right? And if you do the very same maths and you add in a large number of potential points in, for example, the middle bit, and you see where they all go, then you actually realize that you get this 3 by 3 matrix. Now it looks a bit more interesting than our 2 by 2 case earlier on, especially the middle column. It means that if you start in the middle third, there is 0 probability of ending up in the left, there's 0 probability of ending up in the middle, and it all goes to the very high values. And it makes sense if you think about this function f we are using. It was essentially given by 4 times x times 1 minus x. The maximum of this function is at 1/2, and the maximum value is 1. Now if you are around this middle bit where the maximum is, so around 1/2, this is exactly the position of your middle interval if you subdivide 0 to 1 into 3 equal parts. So they're all mapped to very large values, which is represented by this matrix here. You could even subdivide it into 10 subintervals. Now at that point it doesn't make any sense anymore to write all these numbers here, so I chose a color coding instead. So what you can see are small values shown in a dark bluish color and high values shown in a bright yellow color. And everything in between has this greenish hue to it. So we see that there's large portions of this transfer matrix now which are 0. And then there are a few high numbers here, but there are also average numbers in magnitude to the left and to the right. But what can we do with these matrices now that we can calculate them or think about them, giving us the answer to with which probability do we go from where to where? What is in there for us in terms of predicting our real-world problem? It turns out that by using these matrices, you can even go up to infinitely many steps all at once. And the way this works is that you have to calculate this sum. So you have your input vector v, just like before, plus the application of t once, plus application of t twice. So this is all initial conditions have made 2-step through this complicated domains, plus all contributions which have done 3 steps, and so on, up to infinity. Now you might ask, how am I supposed to calculate a product of infinitely many matrices? But it turns out that under certain constraints, this is actually possible. But what you have to do is you have to solve this system for W. So W is the unknown, and it's now here under the application of T. And it turns out there's a whole plethora of theory on how this can be done. And there are specific numerical algorithms to do this. Unfortunately, there's not a time to go into that. But if you are interested in that, please come along for our webinar. The last thing I want to do is get back to our car example. As you might have thought, a 10 by 10 matrix is not quite enough to calculate something complicated as this car. So here, just to show you how far you can take this, the car example has such a T matrix predicting where certain vibrations go through this complicated domain, but it's not 3 by 3, it's not 10 by 10, it's 2.5 million by 2.5 million. And just to give you an idea of the scale, I plotted positive values in red and negative values in this matrix in blue. You might now ask, negative values, negative probabilities to go somewhere? This is due to the fact that we chose a slightly different setup here, and it doesn't work quite as well in terms of a short story in a 30 minutes video, but believe me, it does make sense to also talk of negative numbers here. And if you look at this in set F here, you might just be able to see that in these tiny boxes here, individual pixels, these are your individual numbers, individual contributions in this huge matrix. But this box F here is only this tiny little box, almost not possible to see in here. So it's part of this red band. But this red band, as indicated in this box here, is only this red band if we zoom out a bit further. So this box here is this box. So we zoomed out, we have this larger square here, and this red band is just part of a larger red band. And you might have guessed you have to zoom out even further. So this whole red band here is only this tiny diagonal here. It extends even further, and then suddenly you have this blue bit here. So this blue bit here is this blue bit, and this red diagonal is now here. So this part is now only this part, and you have to zoom out from this square once more. Now this blue bit, for example, here is this blue bit here, and only after this zooming out we see this whole matrix in total. So you need to be very efficient and very careful in the choice of your computer algorithms to work with such giant matrices. But this is also part of applied mathematics, because you deal with real-world problems. Sometimes you just have to take the few mathematical bits you have to rather large dimensions in order to make sense of what's going on. And with this, I want to close. What did we talk about today? I showed you an example from applied mathematics, where we use the mathematical tools in order to predict the behavior of complicated real-world applications. And here we wanted to look at the vibrations in a complicated structure, such as this car. I told you that the way we do this is by looking at where vibrations go. They start somewhere, and then from there on, as time progresses, go somewhere else. So a natural language is that of dynamical systems theory. And in order to give you an idea of what that is, I introduced this much simpler system of the logistic map. Looking at that, we had a look at a few orbits, as they called, at a few initial conditions, and we followed them on their path through time. Then we introduced probabilities. What was the probability if you started on the left-hand side to end up on the left, or to go to the right? And we saw that matrices can play a very important role there by telling us how large these probabilities are. And then by using a computer, we calculated matrices of larger dimensions in order to tell you what's going on in more detail. So by subdividing this interval into 10 sub-intervals, the transfer matrix would look, for example, like that. And as an outlook, I showed you this huge matrix again, which was used to calculate these numbers here. For that, you have to bring lots of skills together. That is mathematics. This is where you get all the matrices from, where you get your understanding of dynamical systems from. But you also need to be able to use a computer efficiently. So this is your numerical analysis, but this is also just writing very efficient, maintainable program code. So you might have seen the odd line of Python. That is something which can get you quite far in applied mathematics if you use the right libraries. I hope I could give you an idea of what applied mathematics can be about. If you're interested and want to know more, please come along to our webinar. Thank you very much.